for all the delays. Thanks for joining us, Kevin. So yeah, this is going to be the introductory workshop. If you have questions at any point, please feel free to interrupt me. Hopefully, all this stuff should be pretty clear because everything else is going to build on top of this. The outline for today, we're going to talk about what deep learning is. We're going to discuss like what we're going to teach you. Then we're going to give you some practical steps that basically work for every single project that you'll do in Launchpad. And then finally, we'll talk about the basic regression models, and we'll go through those using like the 6 steps that we talk about. So we'll start by giving some broad definitions of everything. Launchpad works in AI, which is kind of the ways of making machines intelligent or sort of approximate things that we would describe as human behavior. So this comes in many forms. Deep learning is one of them, but it's not all inclusive. Machine learning specifically is kind of like a subset of AI, where rather than just trying to make computers approximate human behavior, we attempt to do so, but with data. And so AI doesn't necessarily require you to use data. You could, type like hard code decision rules if you wanted to, and that could be counted as AI. But in machine learning specifically, we use real world experience or data in order to improve a computer's ability to perform a specific task, usually with respect to some type of metric. So, on the right here, there's kind of a drawing of like some classification task that the computer gets better at with more data. And then finally, there's deep learning, which is kind of like a subset of machine learning specifically that uses deep graph networks in order to represent, the functions that they try to approximate. And so these normally involve millions of layers and require a lot of computation. So maybe to just summarize everything that I've just said, basically AI is kind of this overarching field. Machine learning is like a subset of that uses data, and deep learning is a specific subset of that uses neural networks. And the Launchpad education program kind of sits within this deep learning bubble. And we can maybe talk about like what you're going to learn and why we decided what we were going to teach you. So the schedule for the semester is as follows. We have the basic introduction today on linear and logistic regression, and that's going to be most of the, the most classical machine learning stuff we'll teach you. Then it kind of just goes down straight into neural networks. So I think next week might be the longest workshop that we have. Then we talk about training models, CNNs, some brief digressions into classical approaches, but then mostly just talking about more advanced neural networks later in the semester. And so if you wanted to ask, okay, well, we're going to learn about a lot of different models. What's behind all of these different models that we're teaching you? Well, there's actually like a lot of different fields of math and theory within CS and statistics. And so as you can see, there's a lot of different things that machine learning builds off of. It builds off of probability theory, discrete math, linear algebra, info theory, statistics, optimization, tons of different fields. But those are all taught by classes, right? So if you want to learn about those things, you should just kind of take some of the classes that I have listed down below. But then deep learning, which is really popular right now and has a lot of exciting results, you can kind of skip over a lot of this earlier stuff and just get straight into deep learning. And so our approach this semester is going to be that, all the other stuff you can learn by taking classes. We're here to teach you the deep learning component, which isn't covered by most classes. And so hopefully that means that, this will be useful for everyone. If you're interested in theory, I'm considering hosting optional theory workshops that will just be done kind of like lectures. And so that's going to depend on how interested people are and how busy other people are. So I might post in the education channel later at some point to see if people are interested in learning more about the theory side of things. So let's get straight into what machine learning is, and we'll kind of formally begin the education part of the workshop. So the goal of machine learning fundamentally is to take some data set of, labeled points. And so in this case, we'll look at the case where the data points are of the form X and Y, where there's some input X. So X is like, the input, and Y is the output. So basically, you want to learn some model that maps all of the X's to the Y's. So a really simple example of this that's probably way overused is that, your input is an image and the output is this a cat or a dog? Something really simple like that. So all deep learning can really be thought of as a way of learning a really complicated function approximator that learns, the function that you want it to based off of the data that you give it. So it's worth noting that this setup isn't always the case, but it's the one that we're going to take for the rest of this workshop, and will work in most scenarios. So yeah, machine learning is basically just learning a function that maps inputs to outputs using some data set. So we can dive into the steps that we follow to do this. The first is obviously to collect the data. And I'd argue that this is probably the most important step that you have when you're learning a machine learning model. And that's because, when you're learning your function f or your model, it's only going to be as good as the data that you put into it. So if you have terrible data, you're going to learn a terrible model. If you have great data, you might not have enough data. So it's really about having enough good data in order to learn a good approximation. And the more data you have, the more complicated models you can learn. And you'll see, if you go back and look at the history of neural networks, you'll find that basically compute and data were what caused all of the innovations, or the beginnings of all the innovations that we see today in AI. Before the data and compute, neural networks were around for 20 years and no one did anything interesting with them. It's because they couldn't train them and they didn't have enough good data. So the second step to machine learning is to take all of this data that you've collected and convert it into a format that machines can actually use. So we call this vectorizing your data. And I've given a few examples of this down below. So let's say that, we're building our cat dog classifier. You can take your image, but, a computer doesn't really know what an image abstractly is. It knows what pixels are and it knows what pixel values are. And so we basically need to convert our image into some representation that we're going to use for our deep learning model. Now, a lot of times images are stored in compressed formats that, you can't really easily send to a mathematical function because they're these garbled representations. So instead, we can take our image and we can convert it into one long vector of all the feature values. So we could, march along this way like this, and then turn around and come back the other way. This is called going in raster scan order, but it's a pretty common technique for taking your image, getting all of the pixel values along those channels and converting them into one long vector. And now you could input this into some model and it could, maybe produce an interesting output. You could also do this for text data. So it's really common to use what are called embeddings, where you basically take words and you associate different vectors with each word. And so you can learn these embeddings in your model, or you can do, there are other ways of doing this. There are pre-trained embeddings, but basically the idea is, you're going to take a word and you're going to convert it to some vector representation, and then that's what you give to your model. So, just remember that your models always need to take in things that computers can understand. And in that sense, if you vectorize your data incorrectly, it'll be hard for the computer to learn something useful.
Okay, wait. If I want to ask questions, can I just interrupt?
Yeah, please, at any time.
Okay, cool. So what was the thing that you said, the process of, traversing the image like this? What was it called?
It's called raster scan order. It's not super important. It's just more of a terminology that's used in some other fields of machine learning. But basically, yeah, there are many different ways of converting an image into a representation that machine learning models can use. And you'll see many ways of doing that actually throughout the training program.
Why would we want to make it a vector? Would it not be easier to work with a matrix?
Yeah, it would. And that's kind of what convolutional neural networks do. But this is kind of just an example. It's not like, necessarily the best way to do it. In fact, you'd normally use it as a matrix instead.
Okay, cool. Thank you.
Yeah. So the next step is once we basically, have our data set, this means that we have vectorized our X's and Y's. So we have, X, Y's that the computer can use. And now we basically want to define some loss function that will tell us how good our approximation is. So if F is like, our model, L says like how good you do on a given prediction. So this function here, L, is just going to measure how close the prediction is to the true value. And there are different loss functions that you'd want to apply for different scenarios. And we'll get into a few of those later in the workshop. But basically, you need some measure that tells your model, how good am I doing? Am I doing good? Am I doing bad? Did I classify this example correctly? Was my prediction very far off? And so basically, we want to find some function such that high loss means that we have inaccurate predictions, and low loss means that we have accurate predictions. And so the goal is basically to take our model. We haven't defined what the model is going to be yet, but we just want to make sure that our model has a low loss overall. And that should imply that it's very accurate. And so choosing this loss function is an important design decision because it directly influences what your model is going to try and optimize. So, after you figure out kind of what your loss function is, you define your model. And maybe a quick digression is that, we put step 3 of choosing the loss function first, because the loss function is kind of like deciding what your model is ultimately going to represent. And so this is kind of like based off of the task, and the model is more kind of based off of the type of data that you have. So yeah, we choose some model by defining it. You can mathematically do this in many ways, but basically we'll just assume from here on out that it's, some type of neural network for most of the training program, or in this case, a linear model. And the models that we'll use in Launchpad normally have parameters. And so we'll denote all of those parameters as W. And these are basically different values. You can think of it as one long vector of values if you want, that determine the output given some input. So, you put it in X, your model takes its parameters, does something with the parameters and X, and then outputs Y. And, often case that's a neural network. And then finally, what you need to do is you need to train your model, right? So I have my loss function and I have my model, which has weights W. And basically what this complicated expression means is I want to minimize the average loss. So if you look here at the equation, this is the label, right? This is the prediction. So I'm putting Xi into my model and it's outputting, f of Xi, which is my prediction for that data point. And then this is the loss of that data point. So you can think of this as like the ith loss, or the loss on the ith data point. And then I'm taking the average over all of those. So it's just the total average loss across all of my data. And I'm minimizing this quantity with respect to the weights. So the idea is that here I'm going to move my weights around until my model gives me the lowest loss that I can. And we'll talk more about how you actually do this in practice. But for now, just assume that we can minimize this function. And then finally, once you're done optimizing your model, the final step is to evaluate the model on another data set. And this is really important. So the idea is that, you collect a bunch of data, you train a model on this data, and it does really well on this data that you've trained the model on. But in machine learning, what we really care about is the ability of our models to generalize to things that they haven't seen before, right? So it's not really useful to have a classifier that tells you if an image is a cat or a dog, but it only works on the images that you trained it on. You want it to work on all images of cats or dogs. So this is why testing on a different data set is very important, because it tells you the real world performance of your model. Because it's going to be biased to be very good at the things that it was trained at naturally. And I think in a future workshop, you guys will talk a little bit more about why we actually do this. So that being said, that's kind of like the first section of the workshop. Are there any questions on this portion before we move on to the actual linear models? Nope, doesn't look like it. Okay. All right, let's get started with linear regression. So let's look at like some example data that we might want to use linear regression on. And the idea here is that we're going to try and build up these models using very simple examples that will hopefully make it clear what we do. And so linear regression is something that, you've probably heard of before. If you are a sophomore or a junior, it's equivalent to like least squares regression. So this might be a little bit of review for you guys. But hopefully the next section will build on top of it, and there will be some natural connection to things that you might not have seen before. So the idea behind linear regression in its most basic form is that you have some scalar y, which is like a label, and we'll only talk about the scalar y case in this workshop, and you have some vector input x, right? So yeah, it's just the standard model form. And as you can see in this first case here, this is just like a regular line that you probably have seen in high school. So like if I were to ask you what the model would be for this data, what would you tell me it would be? Anyone have guesses?
Like y equals x or something.
Yeah.
Yeah. So remember, we want to have some type of weight that we can adjust, but yeah, y equals wx would be a good one, where w and x are just scalars. So the input here is just one dimensional. But now, we have in this other case, which is slightly more complicated, we have two variables, right? We have x1 and x2. So our input is now a vector. Does anyone have a guess as to what the model would be for this case? It's fine if this is something you haven't seen before.
Still w times x, but now they're vectors.
Yeah, exactly. And so we can represent this as, a dot product, w transpose x. But if you haven't seen that before, you can also just think of it as, our data is a vector, so our weights should also be a vector. So we can do this as w1 x1 plus w2 x2, where now we have two weights instead of one weight. And so, each weight kind of determines the plane in a different direction. So yeah, that's kind of what linear data looks like. And so as we kind of discussed before, our model is a linear model, which means, it's a sum of weighted values. So it's linear. And yeah, as before, when the data is one dimensional, so we just have a scalar value for x, you could think of the model as, y equals mx plus b. And one thing that, I didn't talk about before is that we have this extra term out here. So even if my data is one dimensional, as you can see, I have two weights, and this is the bias term. And maybe later, I forget if I included it or not, but there will be some examples of why having a bias term is important. But basically, the idea here is that you don't want to just model, a single line. So if my model was y equals mx here, my line would have to go through the origin, right? I guess I should write this as wx. But if I have y equals mx plus b, I can model something that doesn't go through the origin, right? So this is y equals w1x plus w2. And so being able to model things that don't go through the origin, is pretty important, and it helps increase the generalizability of your linear models. So next, let's define the loss function. So we've kind of, I guess, done it a little bit backwards here, but we started with linear models, so maybe it makes sense to define the models first. The fundamental idea of regression is that, I have my x's and I have my y's, and I want to make sure that my predictions are close to the labels, right? So I want these to be close. And so the way that we measure the closeness of this is using squared loss. And there's some nice theoretical justifications for this that we're not going to get into. But basically the idea is that squared loss actually provides a really good metric for figuring out how close two values are to each other. So for example, squared loss will tell us, how good our linear model does at fitting the data. So you can imagine that on the left here, we have an example of a really bad model. And as you can see, the residuals, or this would be in here, the quantities, my labels, which, are the dots up here, minus the predictions, which are given by the line. So this would be y hat of j. The residuals are very large, right? And that's bad. So we don't want large residuals because that means our error is high. And so basically we want some type of distance metric here. And you could say, okay, well, let me just use yj minus y hat of j. But the problem with this is you can imagine that you run into a scenario where you get negative loss. And that's basically because if you think about it, if my line prediction is here, I guess this is a good example. It's already out here on the slides. The loss here, yj minus y hat of j, is going to be greater than 0 because my, this is less than 0 because my label here, yj, is smaller than the line. And for this data point up here, yj minus y hat of j, the prediction is going to be greater than 0 because my label is larger than my prediction. And so you don't want to have this scenario where, these two can cancel each other out and give you 0 loss. Even more than that, you can imagine now if I just make my line as tall as possible, I can get negative infinite loss. So I could just move my line as far up as I wanted and my loss could go to negative infinity. And, then my model wouldn't be doing anything useful. So you want to make sure that you capture some sense of distance, and, distance is normally done by using the square. This might be a little bit pedantic of a discussion, but I think it's important to make sure that you understand why we use squared loss for prediction tasks. Yeah, any questions on this? Nope. Okay. And also tell me if I'm going too slow and we can speed it up a little bit.
Hold on. For the y hat, is that the predictor? Or
yeah, y hat is the prediction. So you can say y hat of j is equal to f of xj.
This might be a little bit of a nit, but are like the signs, should they be flipped for the like the yj minus y hat j greater than 0, less than 0?
No, so my prediction here is this line, right?
Right.
So this line is y hat of j. So in this case, y hat of j is larger than yj, so it would be negative. In the other case, it would be positive. Yeah. So yeah, and the reason why I'm indexing by j here is this loss is for a single data point, right? Because we can have multiple dimensions of loss. I guess I kind of earlier said we were going to stick with the scalar case, but you can imagine where your label y is equal to, y1, y2, you're trying to predict two things from your data. And now you take the squared loss over all of the dimensions of your output vector. So now we optimize and train this objective function. So this is the same equation as before. You can have the 1 over n scalar out there, to make it the average loss, although you'll find quickly that that really doesn't actually matter. It gives you the same solution either way. And so now we can plug in the squared loss function that we had. And so we sum over all of the different data points. We sum their losses. And each of those losses is given by the sum over all of the features of the labels, right? So this is why we are summing over j as well as I. So j is the feature index, I is the data point index. And this basically gives us the total loss over all of our data points. Most common is this scenario where j, or k I should say, is just equal to 1, where you only have, one output value. But in the case where you have multiple, you need to sum over all of the different output values. And we call this in machine learning like a cost function, and it's normally denoted j of w. It's sort of, this the average loss function over all of your data. And so now we're going to optimize this quantity. But the question becomes, okay, how do we actually optimize this? Well, if you have taken EE16A, you'll probably know that there's actually a closed form solution to this problem given via least squares. But, in deep learning, we don't approach anything with closed form solutions. So we're not going to do it that way here. The way we're going to do this is by using gradient descent. And for those of you scribbling notes very fast, thank you. It makes me feel like, you're trying to learn the stuff, which is good, but also know that like at the end of this, there are notes that I made that's like a summary of this as well. So if you don't get everything, it's not super, super critical. But anyways, I probably should have mentioned that earlier. Gradient descent works as follows, right? So I have my cost function, j of w, and this is just going to tell me how good the model is, like overall. And so basically, I just want to minimize this cost function, make it as small as possible. And I can do this with gradient descent. So the idea of gradient descent is as follows. And we'll look at this pretty simple 1D example. I have some initial guess, which is like right over here. So this, initial weight guess for my model. And then I can take the derivative of my cost function at that point. And what does this really tell me? Well, if the derivative of my cost function looks like this black line here, the gradient or the derivative here at this point is greater than 0, right? And that means that if I move w to the right, then what's going to happen? The cost is going to increase. Then j of w increases because the derivative is positive. With positive w, my cost function increases. And this also means that if I move, w to the left, so I decrease w, then j of w is going to decrease. Right? But the opposite would happen if I were at the other side. So let's say I'm at this point over here, and my gradient looks like that, right? It's the line that's tangent to the curve. So now the gradient or the derivative is less than 0. And if I increase w, what's going to happen? As you can see, the cost function is going to go down, and the opposite is true if I decrease w, the cost function is going to go up. So what does this basically mean? Well, this can be summarized as follows. If my derivative is positive, then I want to go in the negative direction. And if my derivative is negative, I want to go in the positive direction, right? So all I basically should do is I should move my weights in the opposite direction of the derivative. And that's exactly what this update equation says. So basically all I'm going to do is I'm going to take, my whole model, j of w, or my whole model, and its cost function, j of w. I'm going to take the derivative of that cost function with respect to the weights at the current location I am. So this is my current guess right here. And then I'm going to update my guess by moving in the opposite direction of the derivative. And I can do that by basically just taking my derivative and moving a small step in that direction. So if my derivative was, positive, I take a small step in the negative direction, and I'd update my weights, and now I'd be over here. So this would be, weight vector at time 0. This is weight vector at time 1. And now, I'd have some new weights, and I can take the derivative again. So now I take the derivative again, and I see that, oh, my cost function still gives me a positive gradient, so I should move again in the negative direction. And then I update my guess, and this is W2. And I can repeatedly do this until, hopefully I get close enough to this bottom point of the function, which we could call W star, like, the optimal weight value. Will I ever actually get there? Well, you'll see perhaps in some later talks, and maybe part of this one, that, this isn't always a perfect process, and you don't always get the optimal solution, but you should get a pretty good solution by doing this over and over again. Any questions on this? Yeah.
What is j supposed to represent here? The cost function?
Yeah, so j is the cost function.
Okay, cool.
It's just a simpler way of writing, like the average loss as a function of your weights.
Okay, cool. Thank you.
Yeah. So the idea is, if you have the minimum cost value, you have the most optimal model you could, for the model you chose and the loss function that you chose and the data that you have.
Is there a good way to approximate what like a good alpha is, or is that just something you kind of guess?
Yeah, it's called a hyperparameter. It's something you kind of guess and check. So one of the reasons why you would make your cost function the average loss over all of the data is so that the magnitude of your loss is consistent no matter the size of your data set. So there's some things that kind of mathematically help make your choice of alpha consistent. But yeah, normally it's just chosen by trying a bunch of things and seeing what does best.
Okay.
Yeah, there's not much of a science to that. So we can extend this to multiple dimensions. And so, it's not really called derivative descent, it's called gradient descent. And so the multiple dimension version of a gradient or of a derivative is the gradient. So basically all the gradient of the cost function is like this. And we denote it, with this upside down triangle symbol. Let me write it where there's more space. This is just basically the derivative of j with respect to all of the individual weights. So you can write out all of your weights as a single vector, even if they're not in a single vector. You can just kind of concatenate them together. But as you can see, this is just equal to the derivative of the cost function with respect to W1, the derivative of the cost function with respect to W2, all the way down to the derivative of the cost function with respect to Wn if you have n weights or something like that. So it's just a multi-dimensional version. And now, instead of taking, one step in the opposite direction of your derivative, you take a step in the opposite direction of your gradient. So, your gradient is going to be some multi-dimensional thing. In this case, it might be a little bit hard to see, but if I was at this point right here, my gradient in theta 1 would be positive like that. My gradient in theta 0 would be, it looks like it's maybe a little bit that way. And so I take a step in the opposite direction, and that moves me down on this path here. Okay, any questions about this? Nope. All right. Okay, so now our final step is to evaluate the model that we learned. So basically, we'd use gradient descent to train the linear model that we had, which is basically just optimizing the cost function. And we can evaluate it, and hopefully you do pretty well.
I have a question.
Yeah.
So if you go back to the last slide, right, but aren't there two like minimums on this graph? Does that make sense?
Yes, there are. So this is another issue of gradient descent that maybe we'll talk about in more depth, perhaps at a later workshop. But the idea here is that, gradient descent only does as well as it can. It's a greedy algorithm, right? It looks at the derivative where it currently is, and it takes a step in the best direction for that current derivative, right? So when I start out at this point here, the path that it takes me goes down to this minimum, right? And it just found that greedily. It said at every single step, let me just move in the best direction according to my gradient. So it just does that repeatedly. But you can imagine a scenario where there are many, many of these minima, and you don't necessarily find the best one. You find what's called like a local optima. And so locally, it's the best solution. Globally, it probably isn't the best solution. You can imagine this in a 1D scenario where you have a function that looks like this, right? Where this is the true global minimum. But and this is a local one, so it's not as good. But if I start my gradient descent over here, if I start here, it's likely that I just kind of go down and then I'll reach this local minimum instead of the global one, right? So there are a bunch of techniques to overcome this. Some ways of doing it is basically by injecting randomness into your system. So this is done a lot in practice using mini batches. Another way of doing it is by basically like more complicated techniques like momentum or there are a few others, but basically, by introducing some randomness, hopefully you overcome this. But it's very likely that most of your gradient descent runs can end up in a local minimum unless your function is convex, in which case, this is a convex function. It has one global minimum. So it turns out that, the linear regression problem actually only has one local minimum, and it is a convex minimum, it's a convex function. So it only has one local minimum, and that local minimum is the global minimum. But for neural networks, this doesn't happen. And actually, there's a lot of interesting work that shows that for neural networks, local minimum are actually like, epsilon close to the global minimum. So, there's a question of, do we really care so much if we actually hit a local minimum in a neural network? But that's a more complex topic that perhaps is kind of out of scope for what we're doing. So yeah, the final step of this is we evaluate it. And so we figure out how good our model is. And you do this in practice by looking at the loss and your prediction accuracy on the data. So that was linear regression. Now we'll move on to logistic regression. So just a reminder, linear regression is for the scenario where you want to find, predictions that are as close to your labels as possible. So this is a regression task, right? I just want to get as close to my labels as possible using my model. Logistic regression is extending this to classification. And so rather than trying to exactly predict my labels are going to be discrete instead of continuous. So my labels are going to say, is this a cat or a dog? My labels aren't going to say, 0.5 versus 1, etc. Okay. So what does the data for logistic regression look like? Well, we can look at this case where the data is a scalar. And in this case, my labels y are discrete. So discrete y, and in both cases, they're going to be discrete. And so here's an example where I have, some scalar data. It's not perfectly separable, as you can see. And my y value is going to be 0 or 1. And this means that my, decision boundary is going to be some point in x. So I'm going to choose some value of x, and this value of x is going to try and best separate the data into two classes. And as you can see, it's not perfectly possible for this data set. But the idea is, when x is greater than 2.5, I predict 1. And when x is less than 2.5, I predict 0. And so this is trying to classify this data, although it's not perfectly possible. Here's another example where now the data is two-dimensional. So I have two factors, x1 and x2, and I want to find some boundary that classifies the data perfectly. So, one way of doing this was saying, oh, okay, everything on this side of the data is class 0, everything on this side is class 1. And so the goal of logistic regression is to come up with these decision boundaries to basically decide, where do I classify a data point as label 1? Where do I classify a data point as label 0? And there are a bunch of ways of extending this to multiple discrete classes, although we won't cover them in this workshop. So how do we define a loss function for this, right? My loss function should kind of give me some sense of, okay, for each data point, how well is it classified? And that's what we want to measure. And so if you think about it, the regular loss function that we had, square error, isn't really going to do very well, right? So you can imagine, let's say that I use this as my cost function. Let's just say that it's scalars at this point. So my label minus my predicted value. If I do this, you can imagine a scenario where, okay, my label is 1, right? And let's say that my predicted value is like huge. It's like 1,000. Does that matter? I know that my label is larger than 0. It's going to be a value that's way closer to 1 than it is to 0. Does it really matter that it's so big? This is going to give me really high loss. But maybe that's fine because I'm just trying to say, okay, is my data point 1 or my data point y, is it a 1 or 0? I don't really care about the magnitudes too much. And so the solution that people came up for this is pretty natural, although it can be a little bit intimidating if you haven't seen probability yet. But the idea is that we basically predict the probability of being in class 1. So you can imagine each data point is like a coin flip, right? With some probability, I flip a coin and my data point is either class 1 or it's class 0. But these coin flips aren't all even, right? For some data point over here, the probability of it being in class 1 is probably 0.99999 or something like that. So for all of the data points that are class, I guess I'm mixing the labels up. This is class 0. So the probability of this data point being class 0 should be very, very high. But the probability of this data point, being class 0 should be very, very low. Conversely, the probability of it being class 1 should be very, very high. And so for the data points that we know, we can basically say, okay, because I know that this data point, is an actual data point, it must have probability 1 of being in the class that it is. So it basically means that, the data points that I know are certainly of some class. And for the data points I don't know, I want to make a probabilistic guess based off of my data of how likely they are to be of a certain class. So what we can do in our model to realize this is we can say that, my prediction, my model is now going to predict the probability that my input x is of class 1. So this basically means that, if f of x is close to 1, that implies that, my data point is likely class 1. And you can immediately tell how we come up with our decision boundary from this, right? If my probability is 0.5 of being class 1, I can't decide between the two data points. So if y hat is equal to 0.5, this means you're on the decision boundary. You don't know which class the data point is in, And so it's just equally likely to be either one. You have no certainty. So how do we model a loss function for probabilities? Well, we do this using cross entropy loss. And in this case, since we only have one data point, it's going to be binary cross entropy loss. And so this is probably the most complicated mathematical expression to wrap your heads around that we'll go over this workshop. But the basic idea is follows. Y hat is going to be the probability that my data point is 1. So if y is equal to 1, that means that this first term here is going to matter, right? So if I'm in class 1, this first term matters because I pre-multiply it with a y, right? If my data point is y, or if my data point is in class 1, this second term is going to be 0 because it has 1 minus y, right? So this second term doesn't matter. So now when my data point is 1, I completely live within this term here. And then my loss function is just going to reduce to being the log of my prediction, right? So the log function looks like this. And where this is, I guess it's maybe more useful to draw it like this. And you know that the log of 1 is 0, right? So here's my log function. And so I know that my largest value is going to be here. This is 1. It's going to be less than this. And so as you can see, the lower my probability is, or so the lower this value is, the more negative it gets, right? So if this data point is 1 and I predict a probability of 0.01, my log value is going to be super negative. It's going to be out here. But if I predict, that my data point is class 1 with probability 1, and it actually is a 1, then my loss is going to be 0. So what we do is we take the inverse of this expression. We negate it. And so high negative log basically means high loss, right? And so the right-hand side of this equation is just the exact opposite. Now, if my data point is 0, this first term is going to be wiped out because it has the y term in front. So if the y label is 0, this first term is not going to matter. I live in the second term, and my loss is going to become just the log of 1 minus y hat, right? Which could be thought of as the probability of it being in class 0. So if it's not in class 1, it's in class 0. So 1 minus the probability gets me that value there, the probability of being in class 1 or class 0. And so now it's the same exact analysis. If it's very likely that my data point is a 1, so I predict, if y hat is near 1, then what's going to happen is 1 minus y hat is going to be very, very small, right? So 1 minus y hat is going to be out here, which is going to give me a very, very large negative loss. And so when I negate it, very large loss overall. And what this means is now, I actually don't want this data point that's in class 0 to have a prediction near 1 because it's going to make my loss very large. I want the value to be near 0, and that's going to give me, something close to 1. So maybe this was a little bit, this example was talked about a bit too much, but hopefully it's clear why we use this loss. Okay, now we have our same linear models as before. So this is what we saw in linear regression, right?
Joey, I have a question.
Yeah.
It's in the chat, but
Oh, sorry.
no, you're good. How does this equation differ if you have more than 2 things you're classifying?
And
so
to follow up on that, how would we what would the decision boundary look like if we have multiple classes?
So that's a really good question, actually. It's a little bit complicated to actually draw. I think it's much harder, but there are many, many ways of doing multi-class classification. And so maybe to just give you a quick summary of them, you can basically have a bunch of these, logistic models where you say, okay, class 1 versus class 2, class 1 versus class 3, class 1 versus class 7, and you can kind of combine all of them in intelligent ways to figure out what the class actually is. In that case, you use many, many models, and it's hard to really draw out what the decision boundary could be. You could train a bunch of classifiers that are like class 1 or not class 1. So that's, like n different binary classifiers for each of your classes. The one that we use a lot in machine learning or deep learning is just using basically like multi-headed prediction. So remember in regression, you could predict y1, y2. What you can do in the multi-class case, so this is like, regression, is you can predict basically a distribution over all of the classes. So you could predict sort of, some value for y1, y2, y3, and then you could take all of these values and, the probability of class 1, p of, class 1 or something, in this case would be equal to, you know, the value of your prediction for y1 over the sum of all of your other values. So now I get some probability out of this, right? Because I'm taking the outputs of my model and I'm normalizing them so that they all sum to 1. And now each one of these predictions could be interpreted as a probability, and now you could do a similar decision boundary thing. And your decision boundary for this case would be a little bit more hard to tractably draw because you have multiple classes, but you could kind of figure it out. So you could just do this by, you know, figuring out the points where one of the classes is greater than all of the others. Although, you know, it would be a lot more complicated to figure out, and that's why we kind of stick with the 0 or 1, the binary classification task. But when we get to deep networks, we'll talk about it more. But I don't want this workshop to go on for too long. So we want to talk about it now. So how do we define the model for regression? We had, or for logistic regression, we had this linear model that we used for linear regression, right? But now we want to use it for classification. So the idea is that, you know, logistic regression is still going to be a linear system ultimately. And so we have this nice linear model that works well. But the problem with this linear model is that it predicts between negative infinity and infinity, right? And probabilities are between 0 and 1. So what we want to do is we want to take this linear model that predicts between negative infinity and convert it to a model that only predicts between 0 and 1. And the way that we do this is by using the sigmoid function, which is written out here. And the sigmoid function looks like this curve on the left. And basically what it does is it does something very natural, in fact. It takes everything that's, you know, super, super large and pushes it to 1. It takes everything that's super, super small, pushes that to 0, and at exactly 0. So you could think halfway in between the range of my model. So, you know, 0 is like halfway between negative infinity and infinity. It's going to predict 0.5, which is, you know, uncertain. So the decision boundary for my model in this case now becomes the point, or the points at which my linear model predicts 0. And if my linear model predicts positive, my data point is going to be class 1. If my linear model predicts negative, it's going to be class 0. So I've just taken this linear model and I've repurposed it to use it for classification by just, you know, kind of deciding, okay, if you're greater than 1, or if you're greater than 0, predict 1. If you're less than 1 or less than 0, predict 0. And, you know, there's a little bit more math behind why we actually choose the sigmoid function that we're not going to go over. But basically just know that, like, you know, now my linear model is predicting between 0 and 1. And my new model for logistic regression is just the sigmoid of my linear model. So it looks like that. Any questions here?
Wait, so if you didn't use the sigmoid function, would the binary cross entropy loss thing still work, or would that also?
No, it would not, right? So when we did the analysis in this slide on the binary cross entropy loss, remember that we assumed that the loss values would be capped at 1, right?
Okay.
And also remember that the log isn't defined for negative numbers. So
Yeah,
first of all, the value has to be greater than 0. And also, if my value is greater than 1, now I would get into a territory where the negative log, you know, which looks like this, because I'm inverting it, right? So this is negative log. This would allow me to get a negative loss, right? If I let my prediction values go past 1. And now when I have negative loss, my probabilities don't mean anything. My loss function doesn't mean anything. I can drive this loss to negative infinity if I want to by just predicting as large of a value as I want.
Oh.
So it needs to be bounded between 0 and 1 for this binary cross entropy loss to work. Okay. So optimization. Well, we already taught you gradient descent. So all you do is just run gradient descent. And although now it's not a linear model, so it's a little bit more complicated, it has the sigmoid function in front. You can still run gradient descent because you can take the derivative of anything with respect to this. And we're going to kind of abstract away how you actually do these derivatives because, you know, later PyTorch and TensorFlow will do all of this for you. Yeah, we find the minimum. And so we can evaluate our models and see how well they do. So here's some examples on 1D data and 2D data. So as you can see, here's a good example on the left. This kind of shows you the difference between running logistic regression and linear regression on binary classification with a scalar as the input x. And so logistic regression will come up with a decision boundary that looks kind of like this. So this is, you know, halfway on the sigmoid. So my decision boundary would look like this. Whereas linear regression, because it has this weird loss that kind of is trying to predict as close to all of these, is trying to predict close to 1 for all of these data points and close to 0 for all of these data points, it's going to kind of converge to the average of each of the different classes. And that means that it doesn't actually do very well on this task. And so it's pretty clear that the squared loss is the inappropriate loss function to use for classification. When we look at a two-dimensional example, the logistic regression function is going to give this as our optimal decision boundary. And one interesting thing about the decision boundaries for logistic regression is that they're actually all going to be linear. And you can do some math to show this. But remember that the backbone of our model itself was linear. And thus, we're going to find that the decision boundaries that we get are actually also linear. This is kind of a cool property of logistic regression. And you can kind of see that by the fact that if you set your decision boundary as the point where the sigma or the sigmoid is equal to, 0.5, you'll find that, you can kind of back out some of the math here, and you'll get the point where 0 is equal to your linear function, right? So W1, X1 plus W2, X2. And clearly this is linear, right? So you'll find that your decision boundary is linear. This actually holds no matter what you set the threshold to. But yeah, decision boundary for logistic regression is going to be linear.
So really quickly, you only squash it when you want to classify between 0, when there's like you're classifying between 0 and 1.
Yeah. So for regression tasks, you wouldn't want to do this, right? So for regression tasks, when you use the squared loss, you basically say, okay, I want my predictions to be as close to the labels as possible. For here, I'm not really trying to make my predictions as close to some label. I'm trying to appropriately select a class. So it's kind of a different task that requires a different loss function.
I'm sort of confused as to why it's linear.
Yeah. So maybe I can do a little bit of math here. Hopefully, if this will be the only complicated math that we do. But basically, let's say that I just have the sigmoid function is 1 over 1 plus e to negative z, right? And my decision boundary is where this is equal to 0 or 0.5. And when is this equal to 0.5? Well, this is equal to 0.5 or half when this e to negative z is equal to 1, right? If this is equal to 1, then now, the left-hand side is a half. And so when is this equal to 1? Well, that's equal to 1 if negative z is equal to 0, right? So this is the same as saying z is equal to 0. What was z? Z was my linear model, right? So z, just to jump down here, z is equal to, w1, x1 plus w2, x2, and we said that this is equal to 0, right? And now, what is this? This is a line, right? I can solve for this as, x2 is equal to negative w1 over w2, x1, right? In multiple dimensions, this is a separating plane between the data. But yeah, this is one dimension. Okay, but the question is the world really linear, right? I've taught you all these linear models, so you can do classification and regression for linear models, but is this really useful? Well, I would argue that the world is generally nonlinear, and it's really nice when linear models work, but that's not always the case. So the question becomes, how can we use our linear models to do nonlinear things? So, the world is not linear, but we can actually use the same models that we just talked about to do nonlinear classification. So here's linear regression, right? And this is an example taken from the ML notes that are on my website. The regression task would do very poorly at fitting this data because this data is generated from something that looks quadratic, right? And if I try and fit a linear model to this, it's going to do really terribly because it's not going to be able to capture this nonlinear expression. So, what would the equation for this quadratic be? We can say this is scalar input data and scalar prediction. So the underlying model, if I were going to guess, would look something like this, right? Y equals a x squared plus bx plus c, right? But if you think about what linear regression does, linear regression learns y equals bx plus c. It just learns the linear components. It doesn't learn this nonlinear x squared term. But what I can do is if I take my data and I manually add in this x squared term, as I've kind of done down here, now I can predict another coefficient for this ax squared term. So by just adding this nonlinear component to my data, I can now make nonlinear predictions. Does that make sense? So all I do is I take my linear data here, I transform it to this nonlinear data that has these square terms. And now I'm going to learn a coefficient in front of x1 squared. You know, it'll be like WD plus 1 or something like that. And WD plus 1 will correspond to the coefficient on the x squared terms. And now I can learn this quadratic function. Any questions on this? This is perhaps like the biggest jump that we'll do. And then the same thing can be done for logistic regression models. So now let's say I have data that looks like this, right? It's a circle, or it's two concentric circles. So ideally, the decision boundary that I want to learn, let's put it in green, is a circle that goes like this, right? Everything within the circle is class 0. Everything outside of the circle is class 1. How do I model this with a linear regression model, or a logistic regression model, a fundamentally linear model? Well, what I can do is I can add another feature to my data. I can take my data and I can add a data point that's equal to x1 squared plus x2 squared, right? And that's what I've done here. Or to make it even easier, you know, you could do the square root of this and it would just be the distance from the center of the origin. So this new feature here is going to correspond to, you know, the distance from the origin in some sense, right? So each data point now has a distance value. And this is just another feature that I've added. And now when I plot the data with this additional dimension, so z is now my distance dimension, as you can see, my data looks like this, right? So all of the red points are further up because they're further away from the origin, and all of my blue points at the bottom are really close to the origin because that's what, you know, they were according to the distance function. So what does this mean? Now, well, if I look at my data and I want to come up with a linear model that classifies this data, I can do this by just learning a plane that separates my data like that, right? So now I've taken something that, you know, was not linearly separable, and I've made it linearly separable by adding features to my data. So now I can do very nonlinear things with linear regression, or you know, linear models, logistic and regular linear regression. So that's the end of the presentation. Took about an hour, which is not bad given the number of technical issues I had starting it. So sorry about that. But yeah, this is it for this workshop. And then maybe before we end here, I'll send the notebook to the Slack channel and the notes that kind of summarize all of this. But yeah, are there any questions? And then so if you're interested in learning more about theory, you know, if we start these, it'll probably be after like October 5th or so, because I have some deadlines around then, so I can't do it. But basically, there's a bunch of different topics that go way deeper into the things that we covered in this presentation. So, you know, there's you can interpret all of machine learning using probability, which is pretty cool. You can learn why we actually use squared loss for regression models. You can derive the closed form solution to all of the linear models that we have. You can talk about all the more complicated versions of gradient descent, multi-class classification, etc. So yeah, we can cover those at a later time if people are interested. But this is only something that I'm willing to do if a lot of people are interested in doing it, because it does take up a bit of time. It's not part of the normal education program. So yeah, that being said, any questions on this? Yeah. So know that, like, will we cover RL? I think the new member education program goes very briefly into RL. It will be covered in the application series. So I'm actually teaching both of the RL workshops because that's what I kind of work in. So we'll cover advanced RL there, very basic RL, I think, at the end of the fundamental series. But RL kind of, I think, requires a lot of build up in order to really understand. So it's not as accessible as some of the other topics. Yeah. Yeah, cool. Any questions maybe? Should I just send you guys the notebook now, and then you can kind of play around with that and see if you have any questions initially getting set up? Okay, let's do that. And then if you have any other questions, just feel free to unmute yourself, and I'm fine to just talk about them. Okay, Zoom.